In the previous video in this series, where I'm investigating the possibility of reverse engineering the hardware and firmware for this Wren computer, I introduced the idea of a project, enlisting the help of anyone that wanted to get involved in both the reverse engineering of the firmware for this machine, and also that I was looking for donor for reverse engineering the PCB. Got a comment saying that there's no need to take all the components off the board to reverse engineer it. I have to say I've never actually done that before either, but having now worked on these Wren boards for quite some considerable time, it is, in my opinion, by far the best approach. It wouldn't take very long to get the components off the board, and the amount of time that would save compared to trying to buzz out this board, it's a no-brainer. It's so much more straightforward. Also, there's no direct easy access to some of the pins on some of the components, and being able to see through the board. The way I would go about this is scanning both sides and then doing a through board scan as well, which is basically you shine a bright light through the board so you can see both sides at the same time, in effect. And the reason I'm sort of saying this is because these boards have had so many faults. Unfortunately, when these are stored, the machines are generally stored face down, and that means that this end of the board is upwards, and when the battery, which is in this corner, starts leaking, it takes out this entire side of the board. There's a lot of open tracks corrosion on this side of the board that I deal with when I'm repairing these machines. There are other issues as well, that it would just be so much easier to take all the components off. It'll take a day or so to get all the components off, and then at the end of the process I can of course refit all the parts and use sockets and hopefully get a working board out of it. Bearing in mind the boards don't work to start with, so it would still be a kind of a repair as well. So I'm still looking for that, but that's the reason for taking that approach. It's not something I'd normally recommend doing, but in this instance, as I say, having spent so much time working on these, it does seem like it's by far the best method for this. So back onto the current project, and what I thought I'd do in this video is go through in a bit more detail the reverse engineering of the firmware, how you can help if you want to get involved, and the approach that I want to take for the reverse engineering project, because it is going to be quite complex. Looking through the firmware, let's have a quick look at this. This is one of the, there are two 8K ROMs on this. There is about 400 pages of firmware, but I've never seen firmware with so many return instructions. And usually browsing through and looking at the return instructions allows you to break the firmware down into its various blocks, but I think there's something like 300 or 400 return instructions in this firmware, so very convoluted code. It's kind of what you do when you're trying to maximize the available ROM space that you have, and that's fairly typical for machines of this era where ROMs were quite expensive, so manufacturers tended to absolutely cram as much code into them as they could, and I've done the same myself, but it does make reverse engineering it very difficult. So I thought I'd go through the way I'd like to approach this, and also, as I say, how you can help if you want to get involved. So the easiest way to start with something when you're faced with this, because there are of course a lot of different in-out devices on this board, so there's a lot going on. And the main thing I'm interested in at the moment is the floppy drive controller, so we may as well start with that. And looking at the data sheet for that device, there are various lines that we can make use of to try to trap certain events in the firmware. So the first ones, if you're not familiar with this, I won't go into too much detail, but in this machine the floppy drive controller is using its own internal data slicer. I'm fairly convinced now that all the ICs I have here have one fault or another, which is why this is not currently reading any data from the floppy drive. It is reading data, but not any sensible data. It's not coming out as properly constructed data. It's just random bytes that it seems to be feeding out. But what we can do is try capturing some data. So what we have, of course, is a read enable, so we can make use of that to determine when we're trying to read data. We have a chip select, which of course we can also use to determine when this particular device is being accessed. We have a data ready output, which it's not always used, but in this instance it is used because the internal data slicer is being utilized. We have an interrupt request output line, and we have these two lines here. They're labeled A0 and A1, but they are register select lines, so they select the internal register within this device. The one we're interested in at the moment is the data register, and that is accessed when these lines are both high. So what we can do, incidentally, before anyone comments, yes, I have calibrated these chips. They need calibrating on each board you put them on. That's what this pot down here is for. It calibrates the pulse width, so I have done that, and they do all calibrate. All four devices I have here calibrate, but none of them seem to put out any sensible data. So I'll move the camera, we'll look at the logic analyzer, and then I'll start going through the reverse engineering process for the software. Okay, so looking at the analyzer screen, I've set up the trigger here. I want to look at capturing data that's coming out of the floppy drive controller chip, and I want to look at or try and capture data coming out of the data register. So that is when the A0 and A1 lines are both high. So these two lines are labeled here as A0, A1, and I've got them as a 2-bit bus, and that's what those lines are connected to. And I also have the chip select, a read enable, and the data ready output line set as well. So the data ready out will go high when data has been presented by the floppy drive control chip. Read enable is an external control line, as is chip select, and they are controlled by the Z80, as are A0 and A1. So this combination will be present whenever the floppy drive controller chip puts data into the data register, and then the Z80 can read that through the data bus. So we'll see if we can capture anything, and what I'm going to do is arm the analyzer and then press the reset button on the Wren, and we should in theory capture something if the floppy drive controller chip is doing anything at all. So press reset. And sure enough, we have captured something. Not really interested at this point in what it's captured, it's the addresses that we're interested in. So what we're looking at here is the address. You can see the lines, the control lines here. We have the chip select data ready out, which has gone high already. You can see that the data ready out, the red line, went high, and that was driven by the floppy drive controller chip, and that was to indicate that it has some data that could be read by the external host. Read enable, the Z80 wanted to read something, and the chip select has gone low because the Z80 wants to access that particular device. So at that point we're looking at the top bus, the blue bus up top, and we look at the address and it's showing OCBF, and then if we scroll across we get to 0B0A, 0B07, 0B08. So that's the location we want to look at in the source code. So I'll just dig that out. Okay, so looking at this location within the source code, it comes into this block here, and we can see that what's happening is it's using HL as a memory address pointer, and it's loading that with a value of FE21H, and then it's loading to that location a value of FF. It's then outputting data from the A register to an address of 28H, which I've done a bit of checking and I'm pretty sure that is the floppy drive controller chip itself. And from that point on it goes into this loop, and if we scroll through the data we've captured, you can see it just keeps going round in a tight circle. So 0B07, we keep going along back to 0B, so it's just going round and round this loop. And so because there's nothing else being done here, so it's not doing anything that would enable it to exit this loop. So it's loading a value into a from this address, but it's not doing anything to directly modify this address. So this tends to indicate that it's waiting for an external event, and the only real way that the Z80 can modify this outside of a direct coded loop like this is using an interrupt. So what we'll do now is assume that this is being modified by an interrupt, and we'll try to capture an interrupt that is being used to modify this address. So what we'll do now is go back to the trigger, and what we can do is say, okay, we're only interested in the interrupt line. So if we go across, we're no longer interested in the DRO line, so I can get rid of that. Same with the read enable line. The chip select line I'm going to leave active because it may well be that the chip select line for this particular device will also be taken low in response to the chip generating an interrupt. In fact, in theory it has to, because that's the only way the interrupt can be cleared. That interrupt will only clear when the internal register in the floppy drive controller is accessed. So what we'll do now is see if that will enable us to capture some data, but first we need somewhere to capture the actual interrupt, and I have the TIN line connected to the interrupt request line of that device, and it will go high when the interrupt occurs. So in theory we now have it set up to trigger on an interrupt. So I'll arm the analyzer, I'll press reset on the Wren. Okay, as you can see we've captured some data, and because I believe this is an interrupt, then we need to look at the point where the address we're going to jump to is loaded. So we're looking for this point here. So looking from the data, so looking at address 80, which is where we've jumped to in response to the interrupt being generated. And if we look at the source code for that address, we can see it's actually a jump to a separate location. So we should have the values C3, AA and 00 being loaded. So if we scroll through, we've got C3, AA and 00, and that should jump us to the destination address that's in this table. In this case it's AA. So our address at the top, as you can see, does indeed jump to AA, and if we find the part of the source code that resides at that address, we can see I've already started commenting this. I've been through this a few times and tested this. Usually I do multiple passes because the board's operating a bit of an odd way at the moment because of the hardware faults. It's not always doing the same thing, so it's acting in a very flaky way. So I'm trying to find the consistent output that it's giving rather than just the spurious ones. but this seems to be the common one. It takes us through, and also it's the only one that gives us the correct values when we start looking through. So at this address we should have a data value of dB, which we do, and the next one should be 28, which again you can see at AB that value is 28, and that takes us into this. And the next instruction we should see at AC is a call to this address. So we should find that of the next few instructions we jump to an address of 0253. So if I keep scrolling through, you can see those values have been loaded, and we do indeed end up at 0253. So I'll pull up that block of code. So looking at 0253, we have a fairly simple function. The way this code seems to be organized is it's, as I said, several hundred small functions that are called from various places throughout the code. And so that's as far as I'm going to take it in this video. As you can see, it jumps around quite a bit and it calls small functions like this. And this really is what I was hoping to get some assistance with in terms of reverse engineering the firmware. Initially it'd be very difficult, of course, to go through and try to make sense of the entire firmware structure, because of course most of you won't have access to the actual hardware. But if we can, as I said, I've broken it all down like this into what I believe are these small sub-functions. So I've broken it wherever there's a return. Now it is possible that there's multiple returns in a given function, but that's something we'll have to figure out later. But what I would like is to have some assistance going through, making sense of these. So the idea would be, for example, this particular block, it modifies the value, as we can see, at XFE30, and it does something to it, something fairly simple, and it would just be writing a very brief comment. I don't need to know the exact inner workings of the particular functions. All the better if that can be commented, but really what we need is at the beginning of each of these functional blocks is a brief description as to what the block does. And in this case it would start off by saying modifies FE30 by doing whatever operation it ultimately does to it, and then later on we can replace the FE30 label with an actual meaningful label once we've figured out what that particular address does. Okay, so that's what I'm looking to do. Is it just a case of going through each of these small blocks, figuring out exactly what's going on. It's a Z80, so it's very straightforward, it's just time consuming, and going through, decoding each of the blocks, small header comment at the top to say what it does, and then it would save me having to go through this, because every time I jump to one of these as part of reverse engineering a different block of code, then I've got to stop and decode this to see what it's doing. Whereas if this was already done, then of course it would save a huge amount of time. So as I said in the previous video, if you want to get involved in this project, then please let me know. I've had a few people contacting me already, so it's looking quite promising. But if you want to get involved, leave a comment or email me.